How many students join? Sorry, I can't see here. Anyway, I can't see here.
attendees.
Yeah.
So
Okay.
15 attendees are there.
Okay,
40.
okay, fine. So then let's continue because I already because some technical issue actually that previous channel actually I was unable to unmute myself. Okay, so what is happening in basically pulse laser deposition? And before the pulse laser deposition, all previous class notes already I have put in the Moodle, so you will get it. So in pulse laser deposition, what is happening? Like actually transport an atom from the target to a vapor or plasma. So vapor or plasma to a substrate. So from the target, first what will happen? The transfer of the material to a vapor or plasma, and then you can see this is a target material. So target material like similar like actually sputtering. Suppose whatever material you want to deposit, exactly the same material, you should have a target material. And from that target material, that actually laser actually what will do, that using the laser that it will vaporize and then plasma will generate, and that is called plume. So in plasma will generate and then it will deposit, and target and the substrate will placed in a parallel manner. Okay. And what is happening after an atom is on the surface, it diffuse according to the diffusion equation that we know. And here that means epsilon d is that activation energy in this equation, and kt is that energy of atomic the species. So this is actually, so atom after coming to the substrate it will diffuse, and then only that in this particular pulse laser deposition the quality of the film will be much better than all other technique. And one sufficient diffusion for atom to fit in that two best sites. Okay. And either use electromagnetic atom or heat the substrate. So that is actually sorry, this energetic atom will be some because this whatever that atom from the target to the substrate is coming, it could be energetic, or sometimes that we need to heat that substrate so that actually it is proper film we may get. Now in pulse laser deposition, what is happening? And so first here, as the name itself is telling that there is a laser. So laser pulse is there. You can see that this is the laser pulse. So laser pulse will be focused, okay, by some lenses, and then focused laser actually around 45-degree angle it will hit on this target material. And then you can see that actually from the target vaporized atom will come out, and then actually plasma will generate, and here that plasma will generate, and then what will happen, that this plasma will actually, I mean through this plasma, that whatever that atom will come here, I mean will actually kind of sputtering, or it will be um, um, kind of superheated, we can say that this temperature will be very high, and those atom will deposit on the substrate. So in an ultra high vacuum chamber, that elementary or alloys or oxide target are stuck at a 45-degree by a pulse, and the focus this laser beam, and the atom and ion ablated from this target are deposited on this substrate. So in this case you can see that ablation or ablated terminology is being used. So this, so that means in sputtering actually we talked about individual atom, but in this case a range of atom or a total entire area actually will be ablated, okay, and are deposited on the substrate. And mostly that substance are actually, I mean mostly the substrates are attached with the surface parallel to the target surface at an target to substrate distance around 2 to 10 centimeter. So from here to here this distance will be around 2 to 10 centimeter. So what will happen then, high energy laser actually it will actually interact on the surface, and then it will ablate the material. And whenever it will ablate, then due to the high energy, there is a will be a plasma generation, and some ablated most of the ablated atoms actually will come to that substrate. Okay, so this is actually, you can see that actually this how this PLD system it looks like. This is actually the target material. So target is very important, and this is actually now question is that when there is a sputtering established sputtering technology, what is the need of the PLD? Let's say the multi-component system, 5 6 components are there. So those are very easily actually can be made by PLD, wherever in sputtering actually may not actually means give the same stoichiometry, but in PLD we can do it very nicely, and quality of the film will be much better than this sputtering. So focused laser actually will actually fall here, and then actually it will what will do, it will actually here ablation will happen, and due to the ablation these atoms, ions, all things will come out, and then actually it will be that plasma, there is a plasma generation immediately in the nearby region, and finally then actually it will be this deposited on that parallel substrate. Okay, so how PLD works? So there are actually, I mean, what are that? This is actually called Excima laser. So from the Excima laser, you can see that this is actually you have some mirror, so that actually it can be focused way, it can be parts. So you have to. So alignment, laser alignment is very important. In case of PLD, you can see that laser will be outside, and then I mean far from this. I mean not at least inside the chamber. It's outside the chamber. This Excima laser, then first laser will fall on a mirror, sometimes two mirror also can be used, and then actually some lenses is there, using the lens that it will be focused on the target. Okay, and this from the target immediately it will ablate, and then ablate means all the product it will be actually convert to the plasma due to this high power of the laser. And then what will happen, then it's a parallel, so whatever ablated region, so that is actually will deposit on this substrate. Okay, so in this case actually target is the important, and in this there is no range, metal, semiconductor, dielectric, any kind of material can be done. Substrate should be small, and laser typically that excimer laser, so excimer laser means actually it's actually ultraviolet, actually its actual wavelength is in the ultraviolet range, and its pulse in nanosecond range. Okay, and the deposition rate is quite high, so around 100 angstrom per minute, and the vacuum actually atmosphere to this ultra high, so it can operate in atmosphere. There are several PLDs are available in actually that operates in atmosphere, and other are actually in ultraviolet vacuum is regime actually it operate. Okay, so this working frequency like 13.56 megahertz and 30.56 megahertz is actually RFID frequency, and then actually pressure in vacuum 10 to the minus 7 millibar. That is actually, this is just example of one application. So this is very high vacuum, as I told that high vacuum also can be operate, and low vacuum region also can be operate. Laser energy 200 millijoule, and laser pulse 3 nanosecond to 150 microsecond, and laser frequency is 10 hertz maximum, and laser wavelength is actually, you can see that these are that range of this laser wavelength can be and this different wavelength is can be used. Now actually I will show you one video, so there actually it will, you can see. So first of all, this I just this is the real apparatus, how is it looks like. You can see this is a, you can see here this is the laser, and this is a very big chamber, and where the deposition is happening. Just one schematic I would like to show you. Yeah. So this is, yeah. So this is actually, you can see that this is the laser. Okay. this is the laser and this is the chamber. Okay, and here that target and this is the substrate. Now how it's happening, I'll just show you. So once again, sorry, yeah. So from here you can see the laser is actually falling here. As I told that sometimes several mirror is required to particular focus this laser. You can see the laser is how, and this is actually lens is there to make it focused, and in that way that this is the opening. Okay, opening, and through this window, through this glass window, it will basically it will go, and here you can see it will fall on this target material. Not fall, it will focus on the target material, and then actually this immediately there will be a generation of plume, and this is actually this plasma generation. Again that this is happening, you can see this is a very fast process. And in this case actually what is happening, that since this is all this whatever that plasma means we know is a charged particle plus atom plus free electron, all range of things will be there, and in this plasma sufficient number of atom, actually ablated atom from the surface will be there, and those atom immediately will come and sit on this substrate. But there are actually in this there is a arrangement of the substrate heating plus this energy also will be high. So hence what will happen, that you can see that when it will come to the substrate, it will rearrange, and that is actually additional advantage. And in sputtering actually, that sputtered atom does not have that much energy, whatever in this case this atom has the energy. You can see this atom is actually coming, and then there is a heating arrangement or it will have this energy. So in that case actually what will happen, you can see that it will rearrange. You can see the rearrange and proper crystal structure form. So another one video I just like to show you. So what is happening, you can see that how this these things is happening when that pulse laser, you can see that this is not a continuous, there is a gap is there, this pulse laser is hitting. So when particular electromagnetic radiation it will hit, and then you can see that this how the deposition is going on. This deposition is going on, you can see, and this is the laser. And as I told, this is a pulse laser, so it's not a continuous, and in this it will actually it will ablate from the target, and simultaneously there will be a deposition on this. And this you can see that these two are parallel, and this is the target material. So here ablated, these atoms are actually, or ablated particles, you can say that is coming and sitting here. Okay, and in this region there will be a plasma generation, and this plasma generation actually will accelerate also this process. So this is actually what happened, that if that pulse laser deposition is done with a, let's say that picosecond laser. So in picosecond laser, what will happen, that due to this energy, higher energy from the extreme top surface, that range of actually it will actually basically these atoms actually you can see that it will all kinds of atom it's actually coming, not the particle, and this one, and it will deposit on the surface. So in this case, surface damage will be less. And you can see that how it's coming and in depositing. So in this case, target hitting will be less. Sorry, just I want to show you one thing. Yeah, I missed one important point here. Just a minute. So this is actually when laser is pulse, a laser deposit with a very high frequency. You can see that actually from the surface actually it's coming, that atoms are coming. So there is actually no hitting on the target. Okay. And also the damage also will be less. So this is actually, but then if laser in nano pulse, so in that case actually you can see that. Yeah. So I'll show you that how it differs when actually this different with different laser. Okay, that is in the slide I'll show you. So then you can understand that there is a plume formation, and this plume you can see from the window. You can see that there is a plume formation, and when plume formation means your deposition started. Okay, so this is the indication of this plume formation. So by physical, by this visual appearance, you can see that there is a plume formation is there or not. So if plume formation is there, means actually deposition starts. Now, what are the advantage of the PLD? Let's discuss. So this is actually very much flexible and easy to implement, and growth in any environment. So in any environment actually, I mean, and this PLD actually, as I told, this is in vacuum, but when is a low vacuum, like actually if you deposit oxide, so some oxygen actually can be purged, and it's a, let's say that in high, not rather than high vacuum, low vacuum regime can be deposited. So that is actually growth in any environment. Similar, if I want to deposit some nitrides like titanium nitride, silicon nitride, so in that case actually some nitrogen atmosphere is preferable. And exact transfer of the complicated material, this is, you can see, highly complicated material. And this kind of complicated material, and we can see this stoichiometry also is actually highly complicated. So this material can be deposited very easily in pulse laser deposition, but in sputtering also, that such a high or complicated stoichiometry is difficult to maintain. Because in sputtering, what will happen, that individual atoms are coming, but in this case actually what is happening, that it's ablated the region directly, it's coming. Okay, and same thing actually it will deposit, and due to its high energy, that I mean crystal formation also much better, and variable growth rate. So growth rate we can change it. Epitaxy at low temperature, so we can epitaxial growth, we can do it. And resonant interaction is possible. So resonant interaction means actually it's a plasmon in case of metal. So it's actually basically that light actually will like electromagnetic radiation. So this photon will interact on the surface, this one of this target material, and that is actually is playing the role. And atoms arrives in a bunches, and allowing for much more controlled deposition that is possible, and greater control of the growth by varying the laser parameter. So laser parameter is very important. Using the laser parameter, and which kind of laser we are using, and what is that actually the pulse of the laser, and what is the wavelength of the laser, that decides actually that quality of this film. But still some challenges are there, like uneven coverage, because sometimes actually it may happen, and high defect or this particulate concentration. If directly that ablated particle can come, so then it, of course, it will not give that smooth film, some uneven, that's why coverage is coming. And if particles come, of course, actually at if atomic deposition and in particular deposition, so particular deposition generally the defect will be more and not well suited for large scale actually film growth. So it's actually malls, very small substrate is required. So if you, I mean, go for actually large substrate or large scale production, this still this technology is actually not that much scalable mechanism, and the dependence parameters not well understood. And now actually let's understand that how this PLD is actually process it's happening. So pulse laser deposition is a growth technique in which, sorry, hello, can you hear me?
Yes, sir. Yes.
Okay, it's okay, audible, right?
Yes, sir. It's
Okay. So pulse laser deposition is a growth technique in which that photon energy, just a minute, sorry. Okay. Yeah. So in this case, what is happening? That is a growth technique in which the photon energy of a laser characterized by this pulse duration. Okay, and the laser frequency. So as I told, the pulse duration and this laser frequency, these two are actually very important. Interact with the bulk material, means the target material, and then a laser pulse is focused onto the surface of a target, solid or liquid. Most of the cases it's a solid in a vacuum chamber and thereby removes the material. So it's actually ablate the material mostly. And the significant removal of the material occurs above a certain threshold, that I mean threshold this power density, and that ejected and that partially ionized material formed a luminous this ablation plume. Okay, so in this case actually this ionized partially ionized material, so ejected partially ionized material, that is actually form this plume, luminous this ablation plume, and you can see that color, so that's why it's called luminous. And the threshold power density required to create such a plasma depends on this absorption properties of the target material, and then wavelength and this pulse duration. Okay, so absorption of this target material, that is also very important, like in case of let's say the semiconductor and dielectric. So this part is important, then only interaction will happen. So and then it is actually need to be actually heat will actually heat, it will be actually superheated and then ablation will happen. So typical for this Excimer laser is a pulse length 10 nanosecond, and for femtosecond Excimer laser it's actually 500 femtosecond. But in most of the cases this Excimer laser is being used and the removal material is directed towards the substrate where it recondenses to form a film. And the growth kinetics of such film depends on this material flux, the repetition rate, growth temperatures, and then the substrate material pressure also important, and the background gas that is actually vacuum or the reactive. You can see that YVCO, that is actually the superconducting oxide material. You can see that there is a plume color, then LSMO, the plume color is different. Again TIN, the plume color is different. So this is a materials property, that what will be that plume color, and according to this what laser we are using. Okay, and now this initial this ablation process and this plume formation. Okay, so this when this photon interact with the matter, and the photon energy is coupled to the lattice through a electronic process. So this is actually, so any electromagnetic radiation, in this case laser, that is actually nothing but the photon, and this photon absorption by a material occurs in general over an optical depth of several nanometer, where the energy in metal is transferred to that electronic system directly, in a non-metallic system typically to the lattice. So what will happen, that actually there is a transfer of the energy, and that is actually it happens in a optical this depth of several nanometer, where the energy in a metal is transferred to that electronic system directly in a non-metallic system. And then electronic relaxation process, these are actually very fast to like and it typically this lifetime of 10 to the power 14 to 10 to the power 13. Next one, the schematic cartoon is there, so this process it will be clear to you. So then metal, for matter, it has been shown that time scale for this electronic energy transfer to the lattice is in the order of 1.5 picosecond, and strongly dependent on this thermal conductivity, specific heat, and that electron photon coupling. So that means one thing is clear: whatever the photon is coming, that need to interact with that with the target material, and according to the nature of the target material, then actually this energy transfer will happen, and it is actually happen when a particular this depth, not all, it's not mostly from the surface. And then this electronic the relaxation is happening with a lifetime of this one. And this is actually this interaction, actually this or the energy transfer, it's actually with this lattice. For non-metallic system, the relaxation time varies between 10 to the minus 12 to minus 3. So then you can see that this relaxation time 10 to the minus 14 to minus 13 is very fast, the relaxation. Okay. So because this is actually free electrons are there in case of metallic system, but in non-metallic system 10 to the minus 12 to minus 3. So whatever the energy, laser energy, it's interact, that laser energy actually immediately it will transfer in case of metallic system, but in case of non-metallic system it takes some time, and this relaxation time is, that's why 10 to the minus 12 to minus 3. Then absorption process occurs on a such shorter time scale compared to this thermal diffusion process, and then which give rise to this vaporization and the plasma formation during the time scale of this pulse duration. So then according to the absorption process on a much shorter time scale compared to this thermal diffusion. So thermal diffusion, whatever is happening, this absorption is happening, electronic absorption is happening very fast, and with that, this actually this vaporization will give rise to vaporization and the plasma formation. Okay, so that means target heating will be less, whereas this immediate ablation will be very fast. So there are two processes. One is that absorption, any material can absorb the light, or any material that thermal heat could be diffused. So in this case absorption is happening, and through that this process is happening. And then vaporization process can be described by this heat flow theory, where the surface temperature of this target at the end of the laser pulse is determined by this light absorption and the thermal diffusivity, and the laser ablation mechanism for this nanosecond and the femtoseconds are different. Now we can see that what is happening here in this case. First, the laser pulse. So laser hit on this substrate. If it's metal, it will have that free electron, means gas, delocalized electron. Then laser will interact. That is actually called that plasmon. But in case of dielectric of semiconductor, that it will be localized electron, and there it will interact. So second, you can see that electronic excitation. So this energy actually up with the interaction, this you can see that electronic excitation, that whatever that generation, this electronic this excitation, electronic excitation, you can see that this will dissipate. And what will happen, that in case of metal it will transfer fast, but that's why relaxation time actually will be fast. But in case of dielectric and semiconductor, it will slow process. Then you can see that it will transfer, that energy will transfer to the lattice. So first is a photon with the surface interaction, and then second this electronic, that you can see the generation of lot of the charge carrier or the electronic excitation we can say, and then this electronic excitation interaction with the lattice, and this energy relaxation to the lattice is 1 picosecond. So energy relaxation to the lattice, so energy will be relaxed to the lattice, and finally that you can see that heat diffusion over this microsecond heat diffusion, and then this when the heat diffusion, then actually this plume formation is there from here. So melting, the tens of the nanosecond evaporation and the plasma formation, and this solidification. And then again the second pulse, if the laser pulse is long or the repetition rate is high, laser may continuous interaction. So there will be continuous interaction this process. So what are that process? Like absorption of the laser pulse in a material, that is the first step, and metal absorption depth 10 nanometer and depends on this lambda of the laser. Then relaxation energy, that electron photon phonon interaction. So electron and the phonon, this interactions, phonon is nothing but the lattice vibration, and then this is actually 1 picosecond. So this is actually in this case this process and this process. Okay, so this and this process, and then heat transfer, melting and the evaporation, then the plasma creation and absorption of the light, this by plasma and the ionization, this absorption of the light by plasma and ionization, and then interaction of the target and the ablation species with the plasma and the cooling between the pulse. So we need to cool it. So I just actually finish it, and the next class maybe I'll continue again with this one. If you have any first question you can ask, and this PPT I'll put it, and also that if you want that video also I'll put it for your better clarity. So in this process is slightly complicated than this sputtering. It's not that straightforward. Here actually interaction between that plasma and the target surface is extremely important. That's why nature of the material, whether the target is metallic, semiconductor or conducting, and what is its absorption range of that particular light, that is also important. And that is one part from this materials point of view. Second, the laser point of view, it's a laser pulse is important as well as laser wavelength is important. That is also decide the interaction with that substrate. Okay, so this is actually will decide this how is that actually this plasma formation or this ablation process. Okay, so I'll continue in the next class, and that if you have a very first question you can ask. Any questions? So, okay, if no questions, then I just wrap up here itself. I'll continue in the next class. Okay, thank you.
Thank you, sir.
Sir,
Yes, please.
Thank you, sir.
I think two question is there, sir. B type.
Sorry. In
Yeah, sir.
okay, okay. So what frequency? So this is actually, already I mentioned that 13.6 actually that frequency actually, that is actually RFID frequency can be used. This one, and laser beam is very coherent. So how will we make sure that material removal is from all part of the target? It's not laser beam, wherever it will be focused, it will be deposit from there only. Okay, so that's why after the deposition you can see the damage of the target material. You can understand from where that basically that ablation is happening. Okay, so it will be actually not necessary that it's like in sputtering. Actually what will happen there, it will hit throughout the substrate and then as a target, but in this case it's not. In sputtering mechanism is ionized argon is hitting on the target, so it can hit anywhere, but in this case wherever I will focus on the target, from there actually it will come out. And visual after the deposition, by visual observation, inspection, you can observation, you can see that from where actually this ablation happened. Okay. Yeah. Any other questions? Okay. So if no questions, then actually I just wrap up here itself. So in sputtering, what will happen? Lot of wastage is there. It will sputter from throughout the substrate, but in this case, it will be highly focused. So here actually wastage is very less, and that's why the semiconducting, particular superconductor material, that is very costly, and those material can be actually deposited very easily by this technique without less loss, without much loss. Okay, thank you. Any other questions? Okay, then no more questions. Just I'll just take the attendance. Okay, thank you.
Thank you, sir.
Thank you, sir.